Welcome to Daily Papers, the podcast where we break down one interesting research paper every day. Today's question: can an AI write a mathematical proof that's so perfect, so airtight, that it's formally verified by a computer?
We're not talking about high school algebra here. We're talking about the kind of math you'd find in a graduate-level university course. It's a fascinating question because large language models are getting really good at math. They can produce solutions that sound incredibly convincing.
But that's the key word, isn't it? Sounding convincing. The authors of this paper point out a huge problem. AI-generated proofs can have very subtle errors, flaws in logic that even a human expert might miss on the first read-through.
Exactly. The AI might skip a critical step or use a non-existent rule, but it does it with such confidence that you just nod along. So how can we be 100% sure a proof is correct? The answer is something called formal verification.
And what is that exactly?
Think of it as the ultimate, most pedantic fact-checker in the world. You write the mathematical proof not in English, but in a special programming language. For this paper, they used a language called Lean 4. Then, a computer program called a kernel checks your proof.
So it's not a human grader who might get tired or miss something. It's a machine that checks every single logical step.
Right, and the result is binary. It's either a perfect 100% correct proof, or it fails. There is no partial credit. This is what the researchers wanted to test. Can today's best AIs produce these perfect machine-checkable proofs?
To find out, they built a new test, or as they call it, a benchmark. This one is called FormalProofBench.
FormalProofBench is a collection of 200 very difficult math problems. They're pulled from graduate textbooks and PhD qualifying exams in topics like probability theory, algebra, and real analysis. For each problem, the AI is given the question in plain English and also the question already translated into the formal language, Lean 4.
And the AI's job is to write the solution, the proof, in Lean 4. But they didn't just ask the AI to write the proof in one shot. They set up a much more interesting experiment.
They did. They gave the AI an agentic harness. That's a fancy term for giving the AI a set of tools and letting it try to solve the problem over multiple steps, kind of like a real student would.
What kind of tools are we talking about?
It had two main tools. The first was basically a search engine called Lugal for a giant library of existing mathematical theorems. So if the AI needed a specific theorem to make a point, it could search for it. The second tool was a code checker. It could write a small part of its proof and run it to see if it worked or if it had errors.
So it could iterate. It could try something, get feedback, and then fix its mistakes. And it had 40 turns to use these tools before it had to submit its final proof.
Exactly. It's a much more realistic test of problem solving. So the big question, how did the AIs do?
The results are pretty revealing. The researchers tested a whole range of the most powerful frontier AIs out there. The undisputed champion was Anthropic's Claude Opus 4.5. It successfully generated a formally verified proof for 33.5 of the problems.
1/3 of the problems. For graduate-level math proofs that have to be computer perfect, that's genuinely impressive. But it also means it failed on 2/3 of them.
It's a classic glass-half-full situation. What's really striking is how quickly the performance drops off after the top model. The second-place model only got around 18.5% accuracy, and it went down from there. So there's a big gap between the best and the rest.
But the most interesting part of the paper for me was why the best model was so much better. They analyzed how the AIs used their tools and found a very clear pattern.
Let me guess, the best models were just better at searching for the right theorems?
That's what you might think, but no, the opposite, in fact. A common reason for failure was that a model would get stuck in a search loop, constantly looking for a perfect theorem that might not even exist. The successful models did something different.
Which was?
They used the code checker tool way more often. They weren't afraid to just start writing the proof, see it fail, get feedback on the error, and then try again. It was this constant cycle of trying, failing, and iterating that led to success.
That feels very human. You don't learn to code by just reading books, you learn by writing code and fixing the bugs. It seems the same principle applies to AI mathematicians.
Absolutely. And this process isn't exactly fast or cheap. The paper notes that on average, it took the AI models over an hour and cost about $1 in computing resources to solve a single problem.
So, what's the big takeaway here?
The big takeaway is that we now have a very rigorous, almost impossible to game benchmark for tracking AI's mathematical reasoning abilities. FormalProofBench shows that the best models are making real progress, but the gap between understanding a math problem in English and translating it into a perfect formal proof is still a massive challenge for them.
But it does feel like we're approaching a threshold. The authors suggest that AI might soon become a practical tool for working mathematicians, like a co-pilot that can help explore ideas and check for errors in real time.
That's the exciting future this paper points towards, moving formal verification from a niche, specialized skill to a standard part of the mathematical toolkit, all with a little help from our AI friends.